Man, what's going on? It's 102. Okay, so you don't have one. You don't have one. Who else? What? Okay, but you have one. Do you have one like hers? Like, do you have a TI? Do you have a Texas Instrument?
Yeah,
You don't? You can share. Share for now. Look, what I'm showing you is not something that you're going to be tested on. You know, I'm not going to ask you to necessarily do this, but I want you to know how to use that calculator so that when you do go to a higher course, you don't spend 30 minutes doing a problem that you can do on your calculator. All right, and and very quickly. So, once you have this one, just make sure y'all give these back to me. You're gonna share? Okay, y'all are good? Okay, so I have a little handout here.
Is it a quiz?
No, it's instructions that you can keep on how to do this.
So I was doing the rate my professor,
Uh-huh.
and I looked at you and someone put a tag underneath it saying if you pick this class you're gonna fail.
If you come to class, you're gonna fail. At least they didn't say that. Just keep it. I'll get them off the tables at the end. Okay, so look. If we're trying to solve a system of 3 equations, 3 unknowns,
I remember this for the most part. I remember this from. I think we did this near the end of the year.
let me first say that on the problems we were doing last class, we did not have X, Y, and Z. We had like A, B, and C. So for us, if we had a problem that looked like this, 3A plus B plus C equals 4, and then 2A minus 4B minus 2C equals 2, and then A minus B minus C equals 0, that's what we would have been looking at, okay? But the method is the same on how to solve these systems. So on these instructions, the first thing you want to do is you want to transform this system of equations into what we call a augmented matrix. You don't need to know anything about matrices or anything like that. This is just to get you to be able to input this into your calculator properly. So what we do is we identify all the coefficients. We have a 3 here, we have a 1 here, we have a 1 here, and then we have a 4, right? We have a 2, negative 4, 2, and 2. And then 1 here, negative 1 here, negative 1 here, and then 0. So we just write that without any of the letters. And this is called an augmented matrix. And what we need to understand about the augmented matrix is just that there really is equal sign in here, right? And that anything in this column is an X, anything in this column is a Y, anything in this column is a Z, okay? Now, all the Texas Instrument calculators have a function that's built into it that is this function RREF. And it stands for reduced row echelon form. That's what it is, reduced row echelon form. And you need to call that function up into your calculator. So every calculator is a little bit different. It's either going to be in your math menu or in your matrix menu. So what I'm going to do is just kind of go around and see if you can find it. All right? So I thought y'all were sharing.
I already got it.
Yeah. Is that it, right? Then you hit enter?
Yes. How did you input the matrix?
A second matrix.
Yeah, then you scroll to the right.
Wait, do it again?
Yeah, so how do I turn it on?
Okay.
So you turn it on, the
Okay.
second matrix, then you go to edit.
Okay, so all right. So look, the way you're doing it, you have some experience with this in the past?
Yeah.
Okay, so the way I'm showing this is going to work on all the Texas Instruments calculators. The way you're doing it might be a little different on the TI Nspire. So because there's little differences in the way they do things from calculator to calculator, I'm doing it more of like the way a computer science person would do it. They're just going to bring up the function they're going to call this function up and then put the matrix into the function. You are creating the matrix first, then you're going to do the operation. That's fine if you're happy with that, but that's not the way I'm going to show it.
Okay.
Just so you know what I'm doing.
Yeah.
Okay, so I'd like for you to try and find, you still need to find this function though. Okay, so who has not found RREF yet? Who has no idea where it is? No? Okay. So you're going to go to the matrix menu, and then math, and then scroll down till you see RREF. Keep going. Nope, one more, right there. And then hit enter. Did you find it? Yes? And was it RREF? Yep, and hit enter and just wait. Did you all find it yet?
Yes.
And did you hit enter after you found it? Okay, oops, there's some other stuff in there. Clear that out. You need to get out of that menu, that matrix menu. You need to get completely out of that. Go second quit. There you go. Okay, so now bring up that RREF again. So go to matrix, and then RREF, then bring that thing up. Yep, okay, so, all right, so look, please pay attention here, all right? Everyone needs to have this and only this on their screen. Are we there? Are you, okay? So, what we are going to do is put this matrix into this. And what it will do is it's going to do the operations that are going to give us the answer. The first thing we have to put in is a bracket, and the bracket is above your multiplication symbol. Y'all see that? What that bracket says to your calculator is you're about to start putting in a matrix. Then you put another bracket, and that tells your computer, here comes the first row of numbers. And you're now going to put these numbers in with commas between them. The comma is above the 7. So type in 3, comma, 1, comma, 1, comma. I'm sorry, I didn't hear you. Above the 7. Okay, after you've finished putting in the 3, comma, 1, comma, 1, comma, 4, you are going to close the bracket out. And that tells your calculator you're done with the first row. Then another bracket that opens up the second row of numbers. And then put in 2, comma. Now be careful here. On this -4, you do not use your minus key. You use the negative key. There's a difference between the two, right? You'll see that you have a negative key.
No minus.
Okay, you have a minus key, and then you have this key right here. This is the one you want to use right there, not this one. So 2, comma, -4, comma, -2, comma 2. Close your bracket. That ends the second row. Open bracket. Do your third row. Not yet. Hold up. Well, I don't know what you have typed in yet. So, did you close this off? And did you close it again? And then parenthesis. Okay? So this closes off the last row. This closes off the matrix. And this closes off the function, RREF. And once you get that, hit enter, and you should see something on your screen.
Shit. No. I give you
Let me catch up. Okay, you should get something that looks like, I don't know, this is what my calculator gave me. It gave me this, it gave me 1001, and then it gave me 010 -1, and then it gave me 0012. Did y'all get that? Anyone not get that? Okay, so what I'd like for you to do now is understand what the heck that means, all right? if we were to write those numbers out into a matrix again, we don't need to do this every time, but I want you to understand what it means. This means we have as our first row 1, 0, 0, 1. The second row is 0, 1, 0, negative 1. And the last row is 0, 0, 1, 2. Right? Now think about what this first row is saying. It's saying that we have what? 1x, right? How many y's? How many z's? Equals 1. So this means x is 1, right? This one, I have no x's, no z's. Y equals negative 1. And this last one, no x's, no y's. Z equals 2. So these are your answers. This is what x is, this is what y is, and this is what z is. Now, that only works if this was 1, 1, 1 across this diagonal. See that? If this was like 1, 1, 0, then you have more than one solution. But most of the time, we're just going to have one. I mean, in this class, we're just going to have one. Okay? Now, you could do this for a system of 2 equations and 2 unknowns also. Or 4 equations, 4 unknowns. Does this make sense, or do I need to go into any more detail? We'll see if we can maybe use this in a little while. All right? All right, what problem did I end with last time? I was looking at, did I do the 2x squared minus x plus 4? No, I didn't do that one, did I? Oh, yeah, we did. We didn't finish it. Do y'all want to finish that one? Okay, 2x squared minus x plus 4. Over, it was x cubed plus 4x. So we had here a rational expression, and we are going to try and do the partial fractions on this. So the first thing I did, what's the first thing that you're doing now when you're looking at these? Do what? Factor the bottom, right? Before that, though, make sure that the power on top is smaller than the power on the bottom. Because if it's not, you have to do long division, right? So we do not have to do long division here. We are going to say that this is 2x squared minus x plus 4 over, factor out just an x, and we get x squared plus 4 on the bottom. Now I said that this right here was a distinct linear factor. And do you remember what we called this? Irreducible quadratic, because it cannot be factored. So I said to you that what you're going to do is put a over x, right? That was kind of like what we had been doing. But for this one, we put the quadratic on the bottom, and on top we put bx plus c. And that was going to be a linear expression on the top of a quadratic. And now we are going to work with this, and we are going to clear the fractions. So we're going to multiply both sides by this denominator. And what happens on the left side? It just cancels out. So you've got 2x squared minus x plus 4. And then when you multiply this one, I'll go ahead and put it in here, x squared plus 4 here, x squared plus 4 here. Here the x's cancel. Here the x squared plus 4's cancel. And so we are left with a times x squared plus 4. Make sure you put that x squared plus 4 in parentheses because the a must distribute through. And then on this one, you still have an x here, right? And that x has to multiply times that, which means I should put the bx plus c in parentheses, and then I'll multiply that x. Now the shortcut method here was when we were trying to kill off one of these, right? Can you kill off anything? Well, I can't kill this ever, right? Because there's no number I can plug in here to make that work. So let's just do the long method. I don't think it's going to take us very long, and now that we have our calculators, we for sure can get that system of equations pretty easily. So I'm going to distribute a through, distribute x through, and get 2x squared minus x plus 4 equals ax squared plus 4a plus bx squared plus cx. And now what? Didn't we combine like terms at this point? So if I combine, I've got 2x squared minus x plus 4 equals, here are my like terms, here are my x squareds. If I put those two together and then factor out the x squared, I'm going to have an a plus b in front, right? So I'm going to put that in parentheses, a plus b, and then put the x squared on the back. And so I've done those two. How about our x terms?
You can't do anything about it.
I just have cx, right? That's it. So I'm put plus cx. And then how about anything that doesn't have an x? Plus 4a. So this side needs to match this side. So this is where we match up the coefficients. So we say that the number in front of x squared here, a plus b, must be equal to 2. The c has to be what? -1. And 4a has to be 4. So let me write that down. A plus b must equal what? 2. And then I have that c must be -1, and I have that a must be, 4a must be 4. Now, I don't think we need our calculators for this, because I know what c is and I know what a is, right? So c is -1 just by looking. A is 1 if I take this equation and divide both sides by 4. And then to get b, I can use this equation right here and get b, because I know what a is, right? So a is 1, so 1 plus b must be 2, subtract b is not -1, b is +1. Okay? So our final answer is that this right here is equal to a over x, so 1 over x, plus b, which was 1, so x, plus c, c was -1, so -1, over x squared plus 4. Make sense? We're done. This is the partial fraction decomposition. Okay, I have one more that I'm going to show you right now. And then I'm going to put up the general notes for this. And then when you look at them, hopefully they'll make a little more sense now that we've gone through some examples. Okay, last one here is 4x squared minus 3x plus 2 over 4x squared minus 4x plus 3. So we want to do our partial fraction decomposition here. Well,
Trying to break down part apart by breaking the middle term.
what do you mean?
Like trying to factor it out by breaking the middle term.
I'm not sure I understand what you mean.
For the denominator, we need to factor that, right?
Oh, to factor it? Well, is that the first step?
I know, for the power.
Okay, so what about these powers?
Same.
They're the same. So what happens if they're the same? I know that if this is smaller than this, I'm okay, right? I know if this is bigger than this, I need to do long division. But what if they're the same? You need to do long division. Okay? So really, the only time you're not going to do long division is if the power up here is smaller than the power here. If they're the same, or if this is bigger than this, then you're going to have to do long division. So I could do long division right now, couldn't I? All right. Well, let's do it. I put the numerator in the division box. I do not have any spaces in here. I don't need to put any gaps in here because I have an x squared term, I have an x term, and I have a constant. On the outside, I get 4x squared minus 4x plus 3, right? And then we ask ourselves that question. We say to ourselves, what do we multiply 4x squared by to get 4x squared? 1. So I'm going to put 1 here. And when I do that, multiply 1 times that, I just place everything underneath. And the very important step now is to change the signs, subtract. So all your pluses become minuses, all your minuses become pluses. And you add down, and what do you get? X minus 1. Right? And then you go and you play the same game. What do I multiply 4x squared by to get x? I stop, okay? Because the power out here is bigger than this one, right? So at this point, this is my remainder. So I put plus x minus 1 over 4x squared minus 4x plus 3. And now I'm going to go do my partial fraction decomposition on this piece and not forget that I had a 1 up there, right? Okay. Now I'm going to do that in just a second. I'm going to do that, but I want to show you something that you'll probably wind up doing at some point in a calculus class. It's kind of a shortcut, and it only works for certain problems. But this one is just glaring. It's just staring at me right now. It's just like it wants me to do this. All right. There's something about this that I need you to see. These almost look the same, don't they? I mean, it's like 4x squared, minus 3x minus 4x, pretty close, 2 and 3. So the main thing is these are the same, aren't they, 4x squared? So just tell me whether or not you agree with this. Isn't this 4x squared minus 4x plus x plus 3 minus 1? What the hell just happened? Okay, 4x squared minus 4x plus 3. What in the world just happened? I recognize that to make these two the same, right, what I would need is I would need this to be a minus 4x, right? Yes? So I just wrote it down, minus 4x, but then I added x. The reason I added x is because what are these two put together? Minus 3x. So I haven't changed the problem, have I? And then here, I would really like this to be a 3. So I made it a 3, but then I had to subtract 1 because it really is a 2, isn't it? So I have not changed the problem. That's the same problem, right? Okay, now watch me rearrange. This is 4x squared minus 4x plus 3 plus x minus 1 over the common denominator, 4x squared minus 4x plus 3, right? Like that. I just kind of rearrange things. And do you see these first 3 terms are the same as these first 3 terms? So what I'm going to do now is break this into 2 fractions. What I'm doing is I'm splitting it right there. It's kind of like this. If I had 2 over 3 plus 5 over 3, then you could do 2 plus 5 over 3, right? Yes? Now, we could go backwards, too. If you have something plus something on top of a single denominator, we can split it back into 2 fractions. I've very, very cleverly, if that's a word, I don't think it is. I've taken like something plus something, and I've split it back into two fractions. And what is this? That's 1. And so I get 1 plus this, right? Which is the same thing. I'm doing the same thing without actually doing any long division. If that seems kind of like weird to you, it should, but just understand that like in a calculus class, that may happen. Like, they'd be like, hey, let's just do this instead of the long division. Okay. We are at that point over there. So let me write that down. I just wanted you to see that, okay? Okay, at this point, I need to just focus all of my attention on the rational expression and ignore that 1 out front. But just remember that's going to be part of our answer, all right? So what do I do with this piece? Now, you can talk about factoring, right? Does the denominator factor? Well, you're trying to come up with two numbers that multiply to be 12, but add up to be -4. Multiply to be this, but add up to be this. I'm using, I guess, what would be considered the AC method, multiplying 4 times 3 and getting 12, and then looking at the coefficient of the middle term. So can you think of two numbers that multiply to be 12 and add up to be -4? 6 and 2? Well,
No, because that'd be
yeah, if they're both positive, then they're not going to add up to be -4. So I'd have to make one of them negative, but then I can't multiply to be 12. So it's not going to work, is it? Do y'all agree? Like, I can't factor this. So if it can't factor, then it's an irreducible quadratic, isn't it? It's irreducible. So this piece right here, very, very important that you understand we are working with that by itself right now. According to the method I shared with you last class, if we have an irreducible quadratic, then what I'm supposed to do is put that irreducible quadratic down here, and then what do I put on top? A linear expression. So ax plus b, is that okay with you? Ax plus b. Now, right now, there's something staring at you. Just look at that for a second and tell me, do you know what a and b are? If the left and right hand sides have to be equal, b is -1 and a is 1. See, look, what I'm trying to get you to see is that when you're doing this and you're trying to do partial fractions, in this particular problem, the process of getting it into a partial fraction, our goal is to take this and rewrite it as this with a linear expression on top, right? But that's what we already have. We already have that, don't we? Linear expression, quadratic, irreducible. In other words, we're done, okay? Like, this cannot be decomposed any further, because what we would decompose it into is exactly what we already have. Like, go ahead, clear the fractions, multiply both sides. What would you say? All right, isn't that what you would do? And then just match it. What's A? 1, the number in front. And what's B? -1. So you would write down 1x minus 1, which is exactly what you had. So we actually don't have any partial fraction decomposition to do here. We still had to do the division, though, okay? So our final answer would be this expression. No more work can be done.
Professor,
Yeah.
how would we know when we're taking it into the right side, when to take a over x and then when to take ax plus b?
Okay, that's a good question. The question that's being asked is, I've done like a over x, and I've done like, you know, bx plus c over something, right? Like, when do you do which? Okay, so maybe y'all can help with this. When do we do just the letter a over something? When this is a linear factor, okay? When it's a linear factor, you can use a over that. Okay, when do we do this? Irreducible quadratic. So this was irreducible. We could not factor this. So we're going to do the ax plus b over this. The reason I didn't use bx plus c is because I wasn't using a for this problem. Now, had there been an x out here, like that, then I would have probably done a over x first, then bx plus c over 4x squared minus 4x plus 3. And then we would have had to have done partial fractions here. We would have had to have gone through the work. All right, I'm going to show you the notes for this, which I didn't want to show you in the beginning because I thought it would make you freak out a little bit if you saw them before we did examples. Because if you read the notes, they look terrifying. Would you mind turning on the projector for me? Thank you. I know you look mighty comfortable there. Top left corner of that black panel, the top left, second button from the top left. I don't know. Does it say on there? HDMI? Okay, and then the light switch, far left light switch. Up, light switch. There you go. Oh, wow, that turned on. No.
Just turn them all off.
Yeah. Wait, you want them off?
I don't want them all. I just want this side off. Yeah. No, put that one back. There we go. Let's do that one. Yeah. All right, a strategy for, all right, don't worry about what it says here, integrating. Let me get, okay. These are the steps right there. So if you have a rational function is something that looks like p of x over q of x. So you have a polynomial on top and a polynomial on the bottom. Then the steps for doing partial fractions are to first inspect the degree of the numerator and denominator, which is what I was trying to get y'all to see, right? If the degree of numerator is less than the degree of denominator, we move on. If the degree of the numerator is greater than or equal to the degree of denominator, we first use long division. Okay? That's what we did. Then, for whatever remains, what we do is we take this p over q and we try and factor out the denominator. Now, we could have a bunch of distinct linear factors. And if we have distinct linear factors, that would mean like x plus 1, x minus 7, 2x plus 3. If these are all different linear factors, then we're going to put like a over one, b over another one, c over another one. But notice in my notes, I don't use a, b, c. I use a1, a2, a3, subscript. Do you know why we're using this subscript instead of just a, b, c? Any ideas why we do that in math? What if my denominator has 100 distinct linear factors?
The alphabet finishes at
I'm going to run out of letters, aren't I? I'm going to have A, B, C, D. I only have 26 letters to work with. So the way mathematicians get around that is they use subscripts. And see, if I use subscripts, I never run out, do I? Okay, so do y'all understand how this just really means for each linear factor, A over it, and then another number, another number? That's good? Now, what happens if you have a repeated linear factor? So if you have a factor down here that repeats itself, so it's either like squared or cubed or fourth or fifth power, remember how I said you had to write it? You put A over that linear factor, then we did B over the linear factor squared, C over the linear factor cubed, and you keep doing that and keep the powers coming up until you finally get to K. So does this make a little more sense now that we've done some examples? See, if I just showed you this in the beginning, this would have looked like crazy, right? Okay, now what if you have a denominator that has an irreducible quadratic factor? Well, if this is an irreducible quadratic factor, then we put ax plus b. We put a linear expression on top over the irreducible quadratic factor. Okay? Now, we didn't do this. What if you, and maybe you can guess as to what would happen. What happens if your denominator has a repeated irreducible linear factor? What do you think you'll do? And start bringing up the powers, just like we did with the other ones. Exactly. So like, let's say we have an irreducible quadratic to the kth power. Then what we would do, where is it? There it is we would have to put a linear expression on top, like ax plus b, over the quadratic, then a different linear expression over the quadratic squared, and then a different linear expression over the quadratic cubed until we get up to that power k. Do you kind of see a pattern here? And that's where we end. We don't go any further than irreducible quadratics. Because you could have cubics now, right? Third degrees on the bottom, but we don't mess with them. All right. I think we should do one more, all right? But for this one, I'm going to use the help of the computer. We're going to reverse engineer a problem. I'm actually going to create the problem on Wolfram Alpha, and then we're going to decompose it. So I want where is it? It's not giving it to me here. I'm going to have to bring out the big guns here. All right, you ready? You're not going to like this. Here we go. We're going to do negative 3x to the 5th minus 28x to the 4th minus 124x cubed minus 334x squared minus 428x plus 238 over x minus 2 cubed times 2x minus 1 times x squared plus 9. Now, I know that that looks like a complete disaster. It's supposed to. Now, I've already done the honors of giving it to you in a factored form. So this is really just to illustrate how we set up the letters over the different factors to make sure you understand what's happening here. Do we have to do long division? No, why not? What's the power, highest power here? 5? Okay, what about the denominator? What's the highest power going to be here? 6. Because this right here, if we cube this out, we're going to get an x cubed here, right? Then this will give us like an x term. So putting those together, we'll get x to the 4th. And then here, x squared, we're going to have an x to the 6th down there. I don't know what it is, but it's going to be this 6th power of x will be my highest power. So I don't need long division because the power here is smaller than the power here. So what I need to do now is I need to rewrite this as, let's see, what is this right here? Repeated linear factor. So I need to start out by doing a over x minus 2 plus b over x minus 2 squared, right? Plus c over x minus 2 cubed. I'm done with that part, right? I'm done with that part. How about this one right here, 2x minus 1? It's just a distinct linear factor, so I just need a letter over that, right? So how about we use d? D over 2x minus 1, okay? And then finally, plus, let's see, this right here, oh, it's irreducible quadratic, isn't it? So for irreducible quadratic, I need a linear expression on top. So how about ABCD EX plus F over x squared plus 9. Oh, wow. All right. I don't intend for us to take this the whole way unless y'all want to. We could use our calculators. I would not test you to do something like this. The point of this was just to make sure you understood how these things break down on this side. You know that next step would be to multiply through by this, right? And what you would have on the left would just be the numerator. And then over here, each one of these certain things would cancel out, right? But you would have some stuff left over. Let's at least do that step, okay? What would I have after I multiply this whole thing times the a? In my left side, I'm just going to put junk here, okay? That's my left side. I don't want to rewrite all that. Okay, I would have a, and then what's still there after I multiply by the LCD?
X minus 2 squared.
I have x minus 2 squared. Two factors of it remain. What else?
2x minus 1.
Okay, 2x minus 1. Anything else? X squared plus 9. That's what would be left in front of the a. The only thing that went away was one factor of x minus 2. And the next one, I'm going to lose two factors of x minus 2. So I'm going to have plus b just x minus 2, then 2x minus 1, and x squared plus 9. All right, plus, now here, all the x minus 2 factors would go away. So I'd be left with just c 2x minus 1, x squared plus 9, right? Plus d, and the only thing that goes away with d is the 2x minus 1. So I still have what? X minus 2 cubed, right? And x squared plus 9. And then on this last one, you have to be real careful here. On the last one, we still have the ex plus f, two terms, so I put them in parentheses. And those two terms get multiplied by everything except this, right? So x minus 2 cubed, and then 2x minus 1. So this times x minus 2 cubed, 2x minus 1. Understand? And then you would have to actually multiply all this out. Again, I wouldn't give you this, and you wouldn't even see a problem like this in Calculus 2. This, again, was to just illustrate what happens with each of these things in the decomposition. If we had, a couple hours, we can mess with this, right? Expand that, distribute, combine, get all that, and then pass an A through it. Then do that here, right? Pass a B. do all that, do all that, do all that. What we're going to wind up with is we'll collect all of our like terms, and we will have a system of equations. How many equations would we have, and how many variables would we have? Well, how many letters are we going after? 1, 2, 3, 4, 5, 6. So you would have 6 equations and 6 unknowns. And on your calculator, you could set up that, system where you have numbers, 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 1, 2, 3, 4, 5, 6. You'd have 6 equations, 6 unknowns, and then you could type everything in, and then hit enter, and it will spit back what A, B, C, D, E, F, what all those answers are, right? Okay. I'm done talking about partial fractions. Unless there's anything else that you want me to clarify or examples you want to see or anything.
I forgot how, but I remember in high school they actually taught us how to do the matrix
Without the calculator?
without the calculator.
You use what's called elimination or Gaussian elimination. So what you start to do is you start to try and get zeros underneath and then diagonally across. And you try and eventually get it to look like what your calculator gets it to look like. And what you're allowed to do is you're allowed to multiply any row by any number, and you're allowed to add any 2 rows together and replace any row with those 2 rows. Those are called elementary row operations for what's called Gaussian elimination or elimination.
I remember in high school you go through like everything detailed. Here you just kind of skim over it. You go through the main ideas of it, right?
I don't know. I haven't taught high school, so I trust you. I don't know what they're teaching in high school these days.
That new math crap?
Yeah, I've seen some pretty weird stuff.
That new math has to make you cringe.
A little bit. I saw one today. I was watching a video on how they're teaching kids to add 9 plus 6. Yes, but like little elementary school, right? So the idea with this new core, this new Common Core, is that what they do is they say, well, these kids they can't handle the idea of 9 and 6. They're better with like 5s and 10s because they start counting these. They learn to count by 2s, 2, 4, 6, 8, 10. Then they learn to count by 5s, 5, 10, 15. So the 5s and 10s they're comfortable with. So what they do is they say, okay, let me see if I can't remember this. All right, so they take this right here and they break down the 6. They say, oh, we realize that that's really 1 plus 5, right? And then they go, oh, wait a minute, but that 1 and that 9 come together, and that's really a 10, and then 10 plus 5, that's easier, that's 15.
That's like a lot of work.
That's what they're teaching. That's what they're teaching.
New math multiplication's even worse.
Yeah, I mean, just imagine, this is just the addition, so imagine with the multiplication and
Multiplication,
subtraction.
Take a simple 2 factors thing and you're going to have a tree like this big for 2 freaking factors.
Yeah.
Like,
How about you just learn it, right? How about you just learn that 9 plus 6 is 15, right? I don't know. And this is nationwide. This is not just in Texas. I mean, this is nationwide, Common Core. Everyone's being taught the same way. It's, but hey.
Well, any public school districts do that. And independent school districts can still get away with not having to do that.
Mm-hmm. All right. Well.
Yeah, I know, even though I don't go there anymore, obviously, the high school I went to, Bernie, they don't do that crap.
Yeah. Some districts have freedom.
I know, let's teach kids the way that actually makes them successful, not the crap that makes them all dumber. I don't know.
Okay. I want to go back and talk a little bit about vectors, specifically the dot product. We didn't quite finish the dot product. So remember the idea of a vector was that in 2-dimensional space, you have some vector out here, we can call it u. And the u1 and the u2 were what we call the components of the vector. And remember, vectors were not the same as points, right? Points are different. So if we have two different vectors, we'll call the first one u and the second one v, v1, v2, then the components of this vector v are v1 and v2. Let me just draw a v out here for you. It really doesn't matter where it is. Why doesn't it matter where it is? What is it about vectors that make them so special? You can move them around, right? And they're still the same. As long as you move them up, down, left, right, you don't turn them or stretch them. So there's two vectors, u and v. We defined in class what was called the dot product. And it was u with this dot between them and then v. And it was a way to multiply two vectors together. And the answer to this is a number. And the number, you get it by doing this. You take the first component here, u1, you multiply it times the first component here, v1, then you add to that u2, v2. That was the formula for the dot product. And we kind of stopped at a point where we were like, well, what does the dot product represent? Like, what does it mean? Like, numerically, what's the significance? Do we even, like, does it matter, right? And I told you that really it does not, the dot product by itself, when you look at this computation, doesn't seem to be very valuable. But there is another formula that I can write down on the board that creates a very, very useful meaning for this dot product. And here's what it is. U dot v is equal to, I'm just going to write it. I'm not going to say what it is. You can tell me what that means. Okay. So what does that mean? The magnitude. So the length of the vector u times, there's a multiplication here even though I didn't write it, times the length of the vector v times cosine of theta. What is theta? The angle between the two vectors. So what I would have to do is I'd have to slide these vectors around and put them tail to tail. So let's just imagine taking this vector, let's just move it up and move it over or whatever, and it would be like that would be v. I can move v without changing what it is, right? Do you all agree that's what it is? So theta is the smallest angle between them. Because there's actually two angles. There's this angle, right? And then there's this angle. And theta is always the smallest one between the two. So theta would be this, okay? So this in some way gives me a formula that involves the angle between two vectors. And that's going to be very useful to us. Can you take that equation over there and can you solve it for theta? How would you do that? Divide these first on both sides, right? So let's do that. I leave u dot v on the left side. Remember, u dot v is that computation over there, right? But it's also u dot v over the magnitude of u times magnitude of v equals cosine theta. And then finally, to get theta out of cosine, what do I need to do? Arc cosine on both sides. So we get our third formula, which if I take arc cosine here, I'll have arc cosine of this. Take arc cosine here, I'll get theta. And I'm going to write it backwards. I'm going to write theta equals arc cosine of u dot v over magnitude of u times magnitude of v, like that. That's our third formula. It really is just this formula written again a different way, but if you want to look at it as two different formulas, you can. All right. Let's see if we can't use this to do something. All right? Example. the points 1, 1, 1, 4, and 5, 4 are the vertices of a triangle. Is this a right triangle? Is this a right triangle? I don't know why I wrote vertices. It's vertices. Okay. Vertices of a triangle. You know what the vertices of a triangle are? It's just the corner points. That's all it is, all right? So I gave you this. These points make up the vertices of a triangle, and I want to know if it's a right triangle or not. Right triangle means one of the angles is 90 degrees, right? And it would be useful to know if it is, because if it's a right triangle, then it follows the Pythagorean identity, and a squared plus b squared is c squared. But is there an easy way to determine whether or not it's a right triangle? Well, here's one thing I need to do, or I can do. I could just plot these points, right? Now, this is the first example I'm giving you, and I wanted to plot the points because I wanted to show you that we'll be able to visually verify our answer. But in general, you won't be able to do this to say yes or no, all right? So the point 1, 1 is here. The point 1, 4 is here. And the point 5, 4 is right up here. And if we connect these, it sure as heck looks like a right triangle, right? And I think we could all just at this point say, yes, it is, right? But it's, again, because this is the first example, I just wanted us to visually be able to see that it is. If we couldn't tell by this visual that it was, like, imagine you had a right triangle that was like this. Right? If I just gave you these 3 points, you wouldn't be able to tell me by looking whether or not it was a right triangle. Here, the reason you can tell me that is because you know that this doesn't move left or right. This point, right, doesn't move left or right. And you know that these 2 points are on the same y coordinate. So you know that this must be 90 just by the points themselves. But you can have right triangles that don't fit like that onto the plane. Understand? So how can we use this information to verify that this is a right triangle? Well, we have a way of finding angles between vectors, don't we? Yes? What we don't have right now are vectors. We have points, don't we? So let's call this vertices A, let's call that vertices B and vertices C. We need to create vectors now. So one vector, if we want to know this angle down here, okay, if I wanted to know that, I would need to create a vector that starts here and ends here, and then starts here and ends here. Right? I would need to create those 2 vectors. If I was interested in this angle, I would need to create a vector that went from here down to here, and a vector from here down to here, and then I'd have those 2 vectors, right? Or if I was interested in this angle, I'd have to create 2 vectors that were going this way and this way. Because we know what the answer is, let's do this angle and show that it's 90 degrees, all right? So how do we create vectors given points? I realize this was given to you before the last test, so you may have like brain dumped this a long time ago. Okay, so if I'm going to go, let's try and create this vector that goes from here to here, and we'll call that U, and then we'll do the vector from here to here, we'll call that V. And you said that to create U, you're going to do C minus B. What do you mean by that?